Ampere's law. So can you remember these two equations we did last time? For a wire which carries current I, the B field created around it is given by mu naught I divided by 2 pi r. You remember this equation from last time? Yes. And also we had an equation for the solenoid. For the solenoid, the equation was mu naught Ni divided by L, right? So although I just asked you all use these equations, we never derived this, right? We never knew how we got these equations. So to derive these equations, we have a law which is called Ampere's law. And this is very similar to the Gauss's law that you saw in electric fields. You remember Gauss's law, right? In Gauss's law, what did we have? We had EA, perpendicular. Then what did we have? Q over epsilon naught, right? Q enclosed over epsilon naught. So if you look at this equation, this is also kind of have the same trend, like they look similar, but they are not the same. So just as we used Gauss's law to find the electric field, we use Ampere's law to find the B field. But there are few differences that we have to like take into our heads. So just like the Gauss's law, here also we go around a loop. We go around a closed loop. For example, let's consider this current carrying conductor. So this example, so this conductor carries current this way. And we know because of the conductor, there will be a magnetic field around it, right? So here, let's say we are going to we are trying to find the magnetic field at a point like this. So what Ampere said was, we have to have a closed loop. Closed loop means something like this. A closed circle or some structure which is closed. It doesn't need to have any specific shape. A closed loop is something like this. And we have to go around the loop, adding up the parallel magnetic field and the length. So here, what we did was we multiplied electric field and the perpendicular area, right? But here what we do is we find the parallel B component and the length corresponding to it. And we keep on doing it to the whole length. So when we do problems, you will see that this part is very easy. Although it looks complicating, it's not really complicating. Okay. So here it's a length, that is the difference, not an area. We go around adding the lengths and multiply the B field by it. And in this side, we have this constant mu naught. And this I here is the enclosed current. It is the current inside your Amperian loop. This is my Amperian loop. So the current inside my Amperian loop in this example is I, right? Let's say I had another current carrying wire going this way. Then what would be my enclosed I? It will be 0, right? If I had another current carrying conductor going this way, I minus I. So they become 0, right? So you have to take the total enclosed current. Just like we did charge in Gauss's law. We added positive charges and subtracted negative charges, right? In the same way, we will add currents in the same direction and subtract currents in the other direction. So are we okay with this equation? So we will learn how to use this. But for now, are you okay with each of the terms? Yes. Okay. So there are two things that you have to know how to derive. So if you know how to derive these two things, then you kind of know how to do any of the problems with enough practice. Okay. So this is the example one. This is more like a theory part than a question, because these two things, example one and the next example that I'm doing, are in your textbook as theory. So we are going to use Ampere's law to find the B field produced by a current carrying wire. Okay, so here I have this current carrying wire. Let's say current is I. And we know if we use right hand rule, B field is like this, right? Okay. So we can choose any Amperian loop we like. But we always like to make our lives easy. So what do? We are going to choose an Amperian loop which is easy to work with. So what is the most easiest Amperian loop to work with? So this is like something that might be useful to you. If you ever see B fields going in circles, for example, this one here, B field is going in circles, right? Choose your Amperian loop as the same thing as your B field, like use the same loop. For example, this one. So this is my B field, right? So what I'm going to do is I'm going to choose my Amperian loop like this. So it is an imaginary loop on top of this circle that I have drawn. So just like the Gauss's rule, here also we try to choose easy ones. Okay, so are you okay with this fact? It is like if your B field is a circular thing, select a circular Amperian loop. It will make your life easy. Okay, so this is my Amperian loop. And B field is also along that. Now I'm going to apply the equation, Ampere's equation. First I will write the equation before applying. So I enclosed. Let's start with this side, because this side is the easy side most of the time. So we have to multiply the B field by the length. This sum sign tells you that you have to keep on doing this throughout the loop. Okay, let's start going around the loop. So can you see that throughout the loop you have the same B field? It's the same distance from the wire, therefore you have the same B field, same value for the B field. So instead of breaking down the circle into small parts and adding it, what you can do is you can directly multiply B by this length of the loop, right? So it's a circumference, 2 pi r. So this makes sense, right? B times 2 pi r is the parallel component of B times the length of your Amperian loop. So you will see when we go to problems that this term is very common. You always multiply B by 2 pi r. Okay, so are we okay with this side? And what do we have in the other side? We have mu naught, it's a constant, and then current enclosed. So what's the current inside our loop? This, right? We have I. This wire is going through the loop, right? So the current enclosed is I. So if I make B the subject, what do I get? Mu naught I divided by 2 pi R. So this is the equation we used last time, right? So you should be able to derive this equation if they ask in the exam. I don't know whether they're going to ask or not, but in past exams, they have asked this. They have asked you to derive it and then use it. So you'll have to do this part. It's easy. Write this, and then this. So are you okay with this? Yeah? Okay. So this is one type of example, and this is the most common example. Most common means where your B field is going in circles. So when your B field is going in circles, your loop is also a circle. Now let's go to the other example that's given in your textbook. So here I have drawn a cross section of a solenoid. You know solenoid, right? This thing. So here I have cut the solenoid into half and drawn a cross section. So we know that we use Ampere's law to find the B field. So that is our main goal in using Ampere's law, to find the B field. So here, if you remember, B field is not going in circles, right? It is going in straight lines. So can we use an Amperian loop which is a circle? It doesn't make sense to use a circle, right? Because our B field is not going around a circle. It's going in straight lines. So if we choose a circle, it's going to make the problem very hard. So we need to choose a loop that will make our life easy. So they have chosen this rectangular loop, A, B, C, D. So we can kind of imagine why they did that, right? Because here this part A to B is parallel to the B field, so they can directly multiply it. And C and D parts, B, C and D, A parts, these two parts are perpendicular to the B field, right? So you don't get any components from these. So 0, 0 from these. No parallel components, right? No parallel B lines to these components. And also we know there's no magnetic field outside the solenoid. So magnetic field outside the solenoid is 0. So it makes sense why they have chosen this square-shaped loop. But my problem is, why did they choose a loop like this? Why didn't they choose something inside it? Why didn't they do something like this? What's the problem with this loop? Anyone? What's the problem with this one? What will happen if loop is like this? Yes, the correct answer is that. Yes, they cancel out. Why? So anyway, we know we get 0 from these, right? Because B field is parallel, perpendicular to these lines. What about these two? From this one, from this component, from this line, we get a positive B times L. But from this one, B field is going this way and we are going this way, right? We get a negative BL. So when we add all the components in the loop, we get a positive BL and a negative BL. They cancel off, right? They just cancel off. So there's no meaning of doing this because we are going to find B and B get cancelled. Useless, right? So that is why we are not choosing a loop like this. Okay, so now we know why we chose this loop, which has a part inside the solenoid and part outside the solenoid. Okay, now I'm going to apply the Ampere's law. So in Ampere's law, what are they asking us to do? We take the parallel components, multiply by the length. Throughout the loop, we do that, and it is equal to mu naught times enclosed current. Let's say there are n loops or n turns here, okay? We will need it later. Okay, now let's start with this. So what are we doing here? We have to go around the loop adding the B times L components. So let's start with A to B. From A to B, B field is this way, right? B field is this way and we are also going this way. We can directly multiply B and L, right? B and L, this is the length. So this is the component we get from A to B. Do we get anything from B to C? No. Why? Because we get nothing from this part anyway, and this part here, RL is perpendicular to the B, right? So there's no parallel component. So from B to C, we get nothing. Then C to D, again nothing. Why? There's no B field outside the solenoid. And then to complete the loop, I have to go this way also, D to A. So we only got a component from this A to B part, right? So we got exactly what we needed, a term with B. Okay, so all of this is equal to mu naught times the current enclosed in our loop. So what is the current enclosed? So we have all these loop turns inside the loop, right? This one, this one, this one, this one. So this set of turns are inside the loop. So initially I said this, let's assume that this is n turns. So actually there are 1, 2, 3, 4, 5, 6, 7, 8. Assume that there are n turns. So the total current inside it is n times I, right? So each turn carries I current. So n times I. So that is the total enclosed current. There are n loops carrying I current, n times I. Okay, so if I simplify this, I get BL is equal to mu naught Ni. B is mu naught Ni over L. So this is the equation we used last time for the solenoid. So these two examples, current carrying wire and the solenoid, those are like theory. Like you have to know them. Yeah, you should be able to derive this. These two, those are the two examples in your textbook. Okay, now that you know how to do this, let's go to our first problem. So this is an actual exam problem from few years back. And I want you to start with part A. So were you able to derive part A again? It is same as what we did before, right? Part A. Okay, so I will start part A. So this section is a little hard section to understand, but when we do few problems, you will see that the same thing repeats over and over again. Okay, for the first part A, so I'll first draw what they are telling. A long wire of radius A. So we have a radius A wire. The same radius throughout the wire. And it carries current I naught, which is equal to 2 amps. And also they are saying current is uniformly distributed throughout its cross section. That means if I draw this cross section like this, so I'm drawing it in a bigger scale. What it means is current is uniform throughout the cross section. So we will need it for the later sections. That is why they're talking about it. So this current I naught is evenly spread out through the cross section. Okay. In part A, they are asking us to use Ampere's law to determine the magnitude of the magnetic field outside the wire. So they're asking us to find the B field of a location outside the wire, right? So that we have done it before. So the R1 is 1.25 millimeters. So we are interested in a location like this. So it is very similar to what we did before, right? So if I kind of draw the cross-sectional view, here is your current carrying conductor with radius A, and they are asking us to find the magnetic field at a location like this, R1. So we know when we use right hand rule, current, the magnetic field is going around circles, right? If we use right hand rule and thumb tells us the direction, shows the direction of the current, and the fingers curl around the magnetic field. So we don't know the direction, but here I have marked an arbitrary direction. I consider it coming out. But what we know is B field is going around circles. So what is our usual thing to do? If B field is going around circles, we are going to choose an Amperian loop also to be a circle, right? So if this is my B field, I'm going to think that my Amperian loop is also this. This is my Amperian loop. Okay. So we are done with setting it up. Now substituting to the equation. So first I'll write the equation B parallel delta L is equal to mu naught I enclosed. So we know throughout the loop, B field and the loop, the length are parallel to each other, right? That is how we chose our Amperian loop, right? Amperian loop and the B are the same, are going along the same circle. So this thing, since it's B is the same at each location around the loop, what I can do is I can write B times 2 pi. What is my radius? R1, right? R1 is the radius that they are talking about. So they're asking us to find the B field at a location like this. So this is the radius of the Amperian loop. Okay. So you will see in other problems also that we keep on repeating this term. This term is very like always we use this term B times 2 pi R. Okay. Now what is the current inside? So this is my Amperian loop. And can you see this whole conducting wire is inside the loop, right? So the current is I naught. It is completely inside the loop. So this is exactly what we did before. Mu naught I naught divided by 2 pi R1. So if I substitute the values, do you know the value of mu naught? I should have given it to you, I forgot. 4 pi 10 to the negative 7. Okay, so you get 4 pi 10 to the negative 7. I know it is 2 amps. I know it is 2. Then 2 pi. What is R1? 1.25 millimeters. We have to convert millimeters to meters. 10 to the negative 3. Okay, so remember this is 3, okay, negative 3 because it is millimeters. Okay, so when we simplify this, I've got the answer as 3.2 10 to the negative 4 Tesla. The symbol of the unit of magnetic field is Tesla. T. So this is an actual exam problem. They usually start the problem with asking you to derive something, substitute. So tell me when you are done with this, and you can do part B till others are done. So people who have done this can start part B and also tell me when you are done with part A. Okay, I will go to part B. So part B. So in part B, they are asking us to calculate the density, current density. So how do we do that? So I'm going to draw the wire in a bigger scale. Okay. So this is my wire with radius A. So this is my cross section. Okay. Cross section of the wire. So they're asking, so this area, I'm sorry. That's how they gave it in the exam, area. What is the density of current per cross-sectional area of the wire? So they're asking in these units, right? So we know current goes through cross sections, right? So when it goes through the wire, in this part, we can see that they say current is uniformly distributed throughout the cross section. So here is the cross section, and I naught is evenly spread out. So how can you find the density? Current density. Current density is the current divided by the cross-sectional area. So I will write it in words. Cross-sectional area. That is how you define the current density. Current density is defined by the current divided by the cross section that it goes through. Here it's this cylindrical this circle, right? This is the cross section. So if I find the cross sectional, if I find J, what do I get? I naught divided by cross sectional area of this circle is pi a squared, right? This radius is a, therefore the area of this circle is pi a squared. So if I substitute the values, 2 amperes divided by pi, what is a? A is 0.5 millimeters. 0.5, we have to convert it into meters. Then we take the square. So when you do this, you get 2.55 10 to the power 6 amperes per square meter. Here we are dividing amperes by meter squared, right? Current by area. So let's use this problem as a learning problem, okay? Because like B and C are very new things to you. So in part B, they just ask us for the current density. Why do we need current density? So when we go to part C, you will see why we need it. So are you okay with part B? Tell me once you're okay with part B, I will go to part C, and I want all of you all to listen to part C because it is very important. Good? Okay. So in part C, they're asking us to find the magnitude of the magnetic field inside the wire. So inside the wire. So let me draw the wire in an even bigger scale. So this is my cross section of the wire. Radius is A, and they're asking us to find the B field of a location like this, right? At 0.3 millimeters. And that is my R2. So they're asking us to find the B field of a location like this. We know there is current inside this radius also, right? Because current is evenly spread out throughout the area. So there is some current inside this R2 radius circle. Therefore, we know there is current, there is B field. From the right hand rule, we know that there is a B field which is going like this. Inside the conductor. So, like I told you all before, if our B field is a circle, our Amperian loop is also going to be a circle, right? We are going to select the same circle. So this is my Amperian loop. So I chose the circle at the location that they are asking us to calculate the B field. They are asking us to calculate the B field at R2 radius, right? So my Amperian loop is here. Now let's try to apply Ampere's law. So I'm rewriting the equation. So I didn't do anything yet. I just wrote the equation. Okay. So this part, This part is easy, right? This part is easy. Why? Because we know we chose our Amperian loop to be same as the B field circle, right? So here what we can do is we can write B times the length of our Amperian loop, which is 2 pi r2. So this is the circumference or the length of the Amperian loop. So if you compare this part with part A that we did before, you will see that this is very similar, right? This section is very similar. Now this is the hard part. What is enclosed? What is I enclosed? Is it I naught like in the previous one? No, right? Because we know the whole cross section has I naught, but we are interested in the current in this part, right? So how can we calculate it? So we are interested in this part. The current in this, in the loop. What should it be? How to find it? So if you remember Gauss's law, when we found the charge enclosed, so similar to that, to find the current enclosed, what we have to do is we have to multiply the area by the density, right? So if we know the density of this whole thing, if we multiply by this area, by the area that we are interested in, we get the current in this highlighted part, right? So current density J gives the current per unit area. And when we multiply by the area of the Amperian loop or the area that we are interested in, we get the total current inside this, right? Current per unit area times the area we are interested in. We get the total current in this part. So here what we need is J times A. And what is my A? The area of the Amperian loop, right? Pi R2 squared. Because I am interested in this area, this highlighted area. So if I rewrite this nicely, mu naught J, what is A? A is pi R2 squared divided by 2 pi R2. So pi will get cancelled, one of the R2s will get cancelled, and we are left with mu naught J R2 divided by 2. So this is very similar to Gauss's law. If you remember in Gauss's law, when the problems were harder, the hard part was finding Q enclosed, right? So here also the problems can be harder when we have to find I enclosed in situations like this, where we have to find the density and then the current. So it's like kind of it's like a formula. You find J and then you find current. You find the density and then find the current in the specific area that you are interested in. So you can substitute the values to this equation. So J is this 2.55 10 to the power 6. R2 is 0.3 millimeters. So once you do that, this is the answer I got. So you can do it and check if you get the same thing. 4.8 10 to the negative 4 Tesla. So I want you to first read the question very carefully and tell me what should be the shape of your Amperian loop. Is it a circle or is it a square-like thing that we did for the solenoid? Okay, so read it carefully and tell me whether it is A or B, whether it's a circle or a square like in the solenoid. Is it A? Another A, I got another A. What else? A. Anyone for B? Okay, so your answer is correct, A. So it is a circle. How do we know it's a circle? So like I said before, here they have marked the B field to be in a circle, right? So I said, if your B field is going around a circle, make your Amperian loop the same. So make your Amperian loop same as the circle. So your Amperian loop will also be a similar thing, right? Something which goes on top of this B. Okay. Okay. So you are good. You figured it out. So I want you to do part A and tell me what you get. Okay. So I will start it. So you have to go around the Amperian loop adding B times L, right? But we know around this circle, they have marked that B is the same. See, they have marked the same B around this circle. So what I can write is B 2 pi r. Because we are going around a circle, right? B times 2 pi r. See, like this term is very common. Once you do few problems, you will see that these problems are very similar. Now, next part is the hard part. Figuring out the enclosed current inside the loop. So, current is going like this, right? So, what is the current inside the loop? So, we have all these turns going in, right? See, we have all these turns. So, they say there are n turns and each turn has current I, right? So, n times I is the total enclosed current inside it. So it's not just one wire, there are n number of wires with current I. So you just add all the i's together. So Ni. So what do you get? B is equal to mu naught Ni divided by 2 pi r. Easy, right? Not that easy. So you can, so what I recommend is redo these problems again. Okay? Then you will see that these are very similar. Okay. So what is this r? This r is the distance from the center to the inside of your donut, right? This torus donut shaped thing. So I'll call it the donut. So it's the distance to the donut. Can you see that r changes from A to B? So r can, here the radius, the circumference is small, closer to A, it's small, and here it's the largest. So I want you to think of this, think of that r can vary from A to B and tell me the answer for B. So for the equation for the solenoid was this, mu Ni over L. So compare it with this equation for the solenoid and tell me if the magnetic field inside it is uniform. So what they mean is the magnetic field here same as the magnetic field here? Is it is it a constant throughout each radius? Is it a constant or not? So I got one answer. I want you to think carefully and tell me if it's uniform or not uniform. Any more answers? Anyone who says not uniform? Maybe you can nod your heads if you're scared to write the answer. Okay. So my answer is not uniform. Not uniform. Why? So this equation gives you the magnetic field inside the donut, right? Inside this donut shaped thing. So if I use this equation to calculate the B field here, I'm dividing by a small radius, right? I'm dividing by something like A. But if I use the same formula to find the B field at a location like this, like here, then I will be dividing by B, right? So when I divide by a larger value, B is reducing, right? So from here to here, when I go from here to here, this way, my B field slightly reduces because the radius is increasing. See, this R changes from A to B. If I take one circle, yes, we have the same R, therefore it is constant. But when we go this way, it changes, right? It is not uniform at each radius. When it goes further away from the center, your magnetic field slightly reduces than when it's here. So from here to here, it reduces. Okay, it's a very tricky problem, but something that they can test you, right? Because the calculations are not that hard. You know this Ni part from solenoids. You know that for a circle, our Amperian loop is a circle. So this question is something which combines everything that you know and also kind of new. And also from the textbook. So this is something that they can test. Here, this might be confusing for you. So because of that, let's call this R1, this thing R2, and this R3. I have used the same symbol RR. Let's use R1, R2, and R3. So as the first step, okay, before doing the problem, step 1, I want you to calculate the current density in this conductor, okay, in the first conductor, and the current density in the second one. First one is this one, right, with the radius A. It's a circular cross section, and the second one is something like this. This is your area, and it has an inner radius of B and outer radius of C. So I want you to find the current density of this one and this one separately and tell me what is the area. Area is, what's the area of a circle? Pi a squared, right? Remember? So for this one, it is pi a squared, area of this circle, cross section. So the hard one is this one, this donut shaped thing. What is the cross sectional area of this? You can think of it as a big circle. There's a big circle with radius C, and they have removed a small circle of radius B from it. Think like that and tell me the area. So very good, I got the answer. So big circle is pi C squared, right? And then the small circle is pi B squared. So this is like you have a big circle pi C squared and then you removed pi B squared from it. So if I arrange this nicely, what I get is pi C squared minus B squared. So pi C squared minus B squared. So in a problem like this, it's good if you can write the densities first before you start the problem. Okay. Once you know the densities, the problem becomes easier. So let's do part A together because we have done part A a few times now. So we are looking at, so this is my small circle, small conductor, radius A, and we are interested in a position like R1. R1 is anywhere which is smaller than A. So somewhere like this, right? So I mark it arbitrarily somewhere smaller than A, R1. So this we have done before, right? Something like this. So if I apply Ampere's law, this is my Amperian loop. I'll call it A loop. And this part of the equation will be B times the circumference of the Amperian loop, 2 pi R1. And in this side, we should have the total current inside the Amperian loop. How to find it? How to find the total current enclosed? You multiply the current density by the area, right? So my current density for this one is J1. And then we multiply by the area we are interested in. So we are interested in this area, right? Of area of the Amperian loop. Because we need the current inside this loop. So what is that? Pi R1 squared. This is the current inside my Amperian loop. So practice this few times, you will see that in almost every problem they ask this. So if I simplify this, I get mu naught J1 pi R1 squared divided by 2 pi R1. So I can simplify this a little further. One of the R1s will get cancelled. So I get mu naught J1 R1 divided by 2. So J1 is something that I introduced, right? The problem didn't have J1 in it, right? So we need to substitute for J1. J1 is given by this. It's something that we introduced. mu naught I naught R1 to pi A squared. So what I did was I just substituted for J1. I just plugged this part here. So are we okay with that? Part A? No? Yes? Kind of? Okay. Now let's look at part B. Part B is easy because they are asking us to find the magnetic field outside A. So this is my A, the inside conductor, and they want us to find the magnetic field here. So this is the theory part, right, that we initially did. So this is my Amperian loop. So B times 2 pi R2 is equal to mu times the current inside the Amperian loop. So we have this I naught completely inside the loop, right? So this I naught is completely inside the loop. So we don't have to even think of doing anything else. We don't have to take parts of it, right? All the I naught is inside the loop completely. So mu naught I naught divided by 2 pi R2. So this is same as the magnetic field outside a current carrying conductor. So if you find this hard, I recommend you to redo this maybe twice. Try to redo this worksheet at least 2 times, then you will see that it's the same thing repeating again and again. Okay. So B is easy, C part is the hard one. So I'm going to draw C part. So this is my inside loop, inside conductor, and then outside I have this donut shaped thing. And the radius is B, and this radius is C. So I'm going to use a different color for the next part to draw the Amperian loop. So they are asking us to find the magnetic field somewhere here. Somewhere between B and C. So I'm going to mark an arbitrary Amperian loop inside this loop, inside the donut. And the radius of it is R3. Okay. So if I apply Ampere's law, this side is easy, right? It is just B times 2 pi R. It is easy, but the hard thing is figuring out the I enclosed. So what is the I enclosed? So let's go one by one. So do we get the total current of this conductor? This one A? Yes, right? We get the total thing from here. So for I enclosed, I get I naught completely from this small one. But what about the donut from this one? We don't get the complete thing, right? We only get part of it. So we need to figure out a way to find the current in this highlighted area. Okay, so before figuring it out, shall we look at the direction of currents? Can you see that the small loop, small conductor carries current in this direction, and the donut-like thing carries current in the other direction? So whatever current we get from this, the donut part is a negative current. So it is a negative one. Now let's figure out how to find it. So the same method means how to find the current? We multiply the current density by the area we are interested in. So I'll call A donut. So J2 is the current density of this whole thing, right? And to get the current in the green part, we have to multiply by the area of the green part. What is the area of the green part? So it is something like this. So I'm redrawing the green part only. Inner radius is B. Outer radius is C. Outer radius is R3. So R3 is this, right? This place. So what is the area of that? So what is the area of this? The green color thing. Very good. So the area is, so A donut. So this area is pi R3 squared. So that is my bigger circle minus the small circle B squared. Pi R3 squared minus pi B squared. So now this gives us the, so I'll rewrite the whole thing. Mu naught I naught minus J2 times this area. So this gives the, when we divide the whole equation by 2 pi R3, we get the magnetic field at R3 inside the donut. Okay, so can you see that whenever we calculate I enclosed, it's the same format that we follow. We multiply J by A. When there are like parts of currents like this, and like in the first one, see, what we did was we always did current density times the area. Here the area was a circle, it was easy. But here the area was a ring like this. So your B will be this whole thing. So mu naught, this whole thing divided by 2 pi R3. So you can simplify it further. So I just included this problem, although it's very complicating and very long, so that you all know how to do any problem in this section. So this is the hardest that they can go. Okay.